So you can tell it's the end of the semester when even look at that. There's a typo right there. How many years has this typo been here, and I've not noticed it? It's liner
Huh.
ODEs. Oh, these are linear ODEs.
Okay.
Revisited. So this is like the extended edition. Okay.
Mm-hmm.
So let's look at linear. We had our first order linear. This was like the second day of class. That was section 2-1. And then we finally got into second order linear. This was chapter 5. Okay, so we did that. And so in general, what an nth order linear is, I mean, if we think about what are the characteristics, the coefficients of y and its derivatives only depend on x. That's sort of what it is. So an nth order linear initial value problem, you have the function up through the nth derivative. And if it's an initial value problem, right? So here we had one derivative, so we kind of think in the background, that means that there's one constant defined, so we have one condition to help pin that down. For second order, we would have two conditions. And to be an initial value problem as opposed to a boundary value problem, we're given information about the function and the derivative at the same point. So once again, what that means is we're given a point on the graph, and then we're given the initial slope. Okay? So if you have an nth order diffeq, then you have n constants defined, so you need n conditions. So we tell you what's going on at the function level up through the n minus first derivative. And to be an initial value problem, you're looking at the same point. Okay? So you know the initial position on the function, you know the initial slope, you know the initial concavity, all that good stuff. Okay? And it turns out, because it's linear, and once again, some of you are taking linear algebra, so you know that when things are linear, they extend very naturally. If you know how 2 by 2 and 3 by 3 matrices work, then you kind of know how n by n matrices work. So all that extends. So, how would we solve an equation like this? So if we look at this equation, the highest order derivative in there is the third derivative. So it's a third order equation. And if I look at the coefficients are just constants. Okay? So this is a constant coefficient third order equation. And now let's take a look at the right hand side. Since the right hand side is equal to 0, this is a homogeneous constant coefficient third order equation. So I think back to chapter 5 when we had constant coefficient homogeneous second order equations, and we sort of think about what kinds of functions would have this property. You're taking a function and you're taking constant multiples of its derivatives, and somehow when you add those up, you're getting 0. So that means that when you take the derivative of these types of functions, you're not really getting qualitatively different functions. They're all going to be within the same family. And so just like we did in chapter 5, we're going to make the assumption that we got a y equal e to the mx. So back in chapter 9, so we're out of Laplace transforms now, where the default independent variable is t. We're back to x's. You stuff that in, we're going to get the same sort of auxiliary equation, ancillary equation, characteristic equation that we had before. When you take 3 derivatives of e to the mx, you're going to get a factor of m each time. And then, likewise. And if I stuff that into the equation, I'm going to get an m cubed e to the mx minus 3m squared e to the mx plus 4 e to the mx equals 0. And since e to the anything is always a positive number, we can factor that out. And then divide it out. And we get down to this. Okay? So the exact same thing is going to happen here in Chapter 9 for constant coefficient equations that happened for us back in Chapter 5. This constant coefficient differential equation is going to admit a polynomial equation. So now we just have to remember how to solve polynomial equations. So of course, we're going to spend, most of the time on the algebra here. Now, unlike Chapter 5, where everything was second order, now we're into higher order polynomials. And so there's things like, sometimes you can factor these if they have a special form or synthetic division. But really, we're trying to figure out the values of m that make this 0. So we can go ahead and fire up Desmos to help us. Because if we're trying to find m's that make something 0, then you may recall from your college algebra, that means we're looking for x-intercepts. So if I look at p of x equals m cubed, let's do x cubed. What was it? Minus 3x squared plus 4. There we go. And we take a look at this graph. Looks like -1 is a root, and it looks like 2 is a root. And the fact that the graph bounces, it appears to bounce at 2, means that this 2 might be of, of a higher multiplicity. So how can we actually check this to be the case? Well, you can use long division or synthetic division to verify this. So let's check that m equals -1 works. So we can do synthetic division, or whatever. So we're going to take the -1, that's our proposed root, and then we're going to copy down the coefficients of m. So I've got 1m cubed, 0m squared, 0m minus 3m squared, 0 m's, and 4. So these represent the coefficients of m in your polynomial. And then we do synthetic division. So we drop down the 1, and then we multiply and add. So the reason this is called synthetic division is because we're always multiplying and adding instead of multiplying and subtracting. So we multiply here, and then we add, and then we multiply here, and then we add, then we multiply here, and then we add. Whatever's in this box ends up being the remainder. And since we get a remainder of 0, we're happy because that means that we've actually found a factor. So m equals 1, if that's an answer to setting this equal to 0, that means that m plus 1 must be one of the factors. So that's the factor theorem. And then what's left over here, the 1, -4, 4, that's the quotient polynomial. And then we can, now this is a quadratic, so we're good factoring that. And there it is. Okay, so this actually proves that m equals 1, or -1, and m equals 2 are the roots on this. If you want a review of synthetic division, let me know. I can find a video. I might do that after class, is just find one of my videos from college algebra and put it up there.
Yeah, since I've never heard of synthetic division.
Oh, okay. It's what all the cool kids do. It's a lot like the Heaviside method. It's a lot like tabular integration. It's just a more efficient way to organize the long division without having to write down all the stuff. So I'll put a video up at some point today. Anyway, the point is, here we go. I can now factor this polynomial, and then I can split it. So either m plus 1 is 0, or m minus 2 squared is 0. So m is -1, or m equals 2. But since it's a quantity squared, this is going to be duplicated. So it's going to be what they say that it's got algebraic multiplicity of 2. And so I come back to my solution then. I'm going to have a C1 e to the mx, so e to the minus 1x, plus a C2 e to the mx. And now I've got a duplicate root. So think back to chapter 5. What did we do if I had a duplicate? I need something that's close enough for the differential equation to accept, but different enough that we're linearly independent. We're going to take that e to the 2x and slap on a what?
X.
X. And there you go. Boom. So it's going to be the same rules we had in chapter 5. Okay. What would the form of the particular solution be to this? So what we got here is we've got the same left-hand side as before, but now we've got the right-hand side. So if we think back to chapter 5, and once again, this is why we kind of reviewed this on Monday. The first step we would always do is we would find the YC, so we get the differential equation equal to 0. And then the second thing we would do, is we'd look for the YP. And depending on what the YP, YP was sort of looking at the non-homogeneous piece, and it kind of depended upon the non-homogeneous function there. So if I look at this function here, this is sine of x plus 7 cosine of x minus 9 e to the minus x. And if we look what is feeding into this, it's a constant coefficient differential equation. That means that I'm trying to guess a function or get a function so that when I take its derivatives and I take linear combinations of its derivatives, namely constant multiples of itself and its derivatives, this is what I'm going to be left with. And if you notice, it's made up of functions, sines and cosines and exponentials. And we know from experience that when you take derivatives of sines, cosines, and exponentials, you get those same sines, cosines, and exponentials. So in this particular case, I could guess what a YP is. So looking at this differential equation, I'm just going to copy it down here so we get everything on the same slide. The step 1, the YC, is what we just did. So the YC would be the solution to this diffie equal to 0. We had C1 e to the minus x plus C2 e to the 2x plus C3 x e to the 2x. And now for the YP, I look at this side. I say, okay, well, I've got sines and cosines, so I'm going to put a sine in there. And remember, even if you just had a sine with no cosine, you'd want to have a cosine in there. Because as you take derivatives of sine, you will generate cosines anyway. And I've got an exponential there, c e to the minus x. But then remember, you want to compare and look to see if anything in your guess is repeated up above. And sure enough, e to the minus x is in the complementary solution. So if I substituted in this yp to figure out these coefficients, and I do the calculus correctly, this e to the minus x term is going to zero out because it's part of the complementary solution. So once again, what do we do when we have duplication? We slap on a what?
X.
Slap on an x. Okay. And then the final solution is the complementary plus the particular. So it's literally the same process. It's the same theory going on in the background. All right, we just have more terms to play with. And there it is. solve using the method of undetermined coefficients. So once again, I'm not going to go through the details here, but what would you do? You would take your guess for the yp, and you would stuff that into the differential equation. And then you would set that equal to, or equate coefficients to these linearly independent pieces. The exact same thing we did over and over again back in chapter 5. So the method of undetermined coefficients is no different than it was back in chapter 5. So once again, we'll go through these details. That's why I think tomorrow I'll just have it a work day, so you can work on whatever. If we were in person for this, we would the first hour we would go through and say, okay, this is what we have to do, and then the second hour people would be just working, filling in these details. What if you have an IVP now? Okay, so step 1, we found the YC. Step 2, we found the YP, in this case using undetermined coefficients. And the one thing you got to remember, step 3, your general solution is YC plus YP. Even though the unknown constants C1, C2, and C3 are in here, you need to impose the initial conditions on your final answer here. There you go. Impose initial conditions on the entire function. Okay. Same thing as before. So if you go through all of that, you're going to get this is your C1, your C2, and your C3 along with your YP. So this was your YP, this was your YC, and now you've determined the coefficients. All right, so this is kind of working backwards just to kind of test to see if we this basically should review all the big ideas from undetermined coefficients back in the old days. So suppose this is your equation you get, right? So once again, auxiliary equation, ancillary equation. I think Zeron calls this the characteristic equation. It depends on what book you're reading. Suppose the auxiliary equation for a homogeneous constant coefficient ODE is this. All right, so clearly someone's been watching out for us because they've already factored it down into these a product of at worst quadratic factors. And that's actually the big theorem from algebra. The real factorization theorem says no matter how big the polynomial you have, you can always break it down into linear products of linear factors with at worst some quadratics. And if that kind of thing sounds familiar, that's the theorem we use in partial fractions. When you have a partial fraction decomposition, you can always break up that denominator into the linear factors, repeated linear factors, and irreducible quadratics. So it's the same theorem. So you'd say, okay, now we kind of go backwards. What's the order of the differential equation? So the order of the differential equation is going to match the degree of the polynomial. So this polynomial, I can go through here and just kind of think about the highest order I would be getting from each of these factors. So I'd have an m squared from here. And here, if I went and multiplied all that out, the highest power of m I'd get would be m cubed. And here, I'd have an m squared, but it would be squared. So it'd be m to the fourth. So if I multiply all this out, I add the exponents, and I'd get, add the exponents. So 5, 4, 9. I get an m to the ninth. So this would be a ninth order differential equation. Okay. What is the form of the general solution? So once again, the intent of this problem is to kind of review all the salient forms of solutions. So let's just set this all equal to 0. And so then I would set each factor equal to 0. So I'd have m squared equals 0. I'd have m minus 1 cubed is 0. And I'd have m squared minus 2m plus 5 squared equals 0. So from m squared equals 0, I'm going to get m equals 0, but I'm going to get it how many times? I got multiplicity 2. So m equals 0 twice. I'm going to get m equal 1 from here. And how many times am I going to get that? Three times. And what do I do with this thing here? So let's just take a look at this quadratic. Of course, we always try to factor it nicely. But if it doesn't factor nicely, what can I always hit it with, Rick?
Quadratic equation.
Yeah, so we'll do that. So let's check the discriminant here. Let's check the b squared minus the 4ac to see what kind of things are going to pop out of this. The fact that the discriminant's less than 0 is telling me we're going to get non-real solutions. So m would be opposite of b plus or minus the square root of minus 16 over 2a. That's 2 plus or minus. The negative flies out, hits you in the eye. Square root of 16 is 4 over 2. So it's going to be 1 plus or minus 2i. And so from this quadratic, we're getting two solutions. We're getting 1 plus 2i and 1 minus 2i. So that quadratic gave us two different answers, but this quadratic itself has multiplicity 2. So I would get 1 plus 2i twice. Whoops. 1 plus or minus 2i, and then 1 plus or minus 2i. Right. So remember, these all correspond. These are all the m's, right? The underlying assumption here I have for all of this is that these are all e to the mx's. So let's see what we get. Let's see if I can fit them all on one line. I don't think I'll be able to, but that's fine. Okay, now when you have e to the 0 x, that's just 1. So I got a c1 times 1, that's a c1 plus. And now I got this again. So once again, what do? If you have duplication, you alleviate the duplication by slapping on a factor of x. So that's the m equals 0. Here, I think I'll color code all of this. Okay, so that's for those. Now for here, we've got 1, 1, and 1. So once again, these are the m's that are going on in these coefficients in the exponentials. So I would have a c3 e to the 1x, and then I've got duplications. Every time I have a duplication, I got to slap on another x. So I slap on an x, and then I'd have to slap on another x. So when you do that, you'd have a c5 what? X squared. plus. And I'm not going to have room for these, but let's go to the next slide and talk about what these are anyway. Let's remind ourselves how these work. So for your m, 1 plus or minus 2 i's, remember when you take e to this, you can use properties of exponentials. You're going to have a real exponential, in this case e to the 1x, times this purely imaginary exponential. And remember, we can use Euler's formula and conjugates. This is going to be e to the x, that's our real part, times, what are we up to constant-wise? C6. C6, there's the sine and the cosine. So the real part of the non-real solution, that goes, and that's the coefficient on the real exponential. The coefficient of I becomes the frequency. All right. So let's put this on the next page. So there's our e to the x times a c6 sine of 2x plus a c7 cosine of 2x. But I'm not done, because that quadratic had multiplicity 2, which means I'm going to have to write this again. To alleviate the duplication, I'm going to slap on an x. Now, you can put the x's on the sines and cosines, or you can factor them out. I'll just put the x out front. There's our c8 sine of 2x plus c9 cosine 2x. And there's our 9 linearly independent parts. We got our nine constants there for our ninth order differential equation. And there it is. Okay. Whoops. So once again, it's really about just reminding you how this stuff works, and then, just blast on into the homework. So we've got some every other odds here. We got every third odd. So get in there. These are all methods. These are either homogeneous or they're all methods of undetermined coefficients. So what we'll do tomorrow is we'll have a work day tomorrow for you to work on whatever you want. You've got one last take home. So on the Laplace. So take home 14. We went through that yesterday. There's sort of an interesting little proof there at the end. So if you didn't watch yesterday's video already, or if you did, maybe you want to go back and revisit it. So take home 14 and test 14. These are basically finish up Laplace. There is no test 15. Take home 15 is going to be on the stuff we're doing now, chapter 9. Guess what? You'll have a Diffie-Q where you have undetermined coefficients, and then you'll have a Diffie-Q where you have variation of parameters. So we'll do variation of parameters next week. We'll finish up early. And then on Tuesday, is it Tuesday, May 8th? Did I get that right or not? No. Tuesday 7th, right? It's Tuesday, May 7th? That's where we'll have our project presentations. If you tune in live, then you can just send me your project and you can kind of tell me, you can narrate it as we go through it. If you can't be here in person, you can shoot a video, upload that video. If you're going to share anything with me, make sure that you click anyone with the link can access this, because when it has me try to log in on Gmail, it's doing my student account. It's not the faculty account, so I won't be able to access it. So if you show up, I really hope people can I know that the attendance waxes and wanes during the semester. It'd be great if you could actually show up on that Tuesday, May 7th, to kind of support your classmates and we watch their projects. Um, Once again, test 15 or take home 15 will be 25 points. Your project's worth 25 points. You're pretty much guaranteed to get all 25 points as long as it's something related to differential equations and you can convince me that you know what you're talking about. That's pretty much what I'm looking for. I'm looking for something that you find interesting in this material that you're comfortable presenting to the class. Okay? All right, thanks for coming, folks. Thanks for coming, Rick. Have a great rest of your day. And feel free to pop in tomorrow or Friday if you have questions.